with the mind maps on carbohydrates, we'll try and brainstorm and remember everything we know about it. So monosaccharides, oligosaccharides, and polysaccharides. Carbohydrates, the most abundant biomolecule on Earth, and certain carbohydrates, for example, sugar and starch, are dietary staple in most parts of the world. So the digestion of carbohydrates is the central energy yielding pathway in most non-photosynthetic cells. And insoluble carbohydrate polymers serve as structural and protective elements in the cell walls of bacteria as well as in the connective tissues of animals. Okay, so carbohydrates polymers lubricate skeletal joints and participate in recognition and adhesion between cells. So the main role of carbohydrates in nature is for storage of energy, structural support, lipid and protein modification, recognition of immunoglobulin, and then cell-to-cell communication. So with the types, you have the monosaccharides, which are simple sugars, disaccharides, and the oligosaccharides, which are short chain carbohydrates, and then we have the polysaccharides, long chain carbohydrates. So you have to know some monosaccharides like D-glucose, D-fructose, D-mannose, D-galactose, dihydroxyacetone, D-maltose, D-sucrose, D-lactose. We'll talk about those ones later. But remember that the classification of carbohydrates could be done based on the number of carbon atoms, the position of the carbonyl group or the functional group. So the functional group, an aldehyde, and then that's of a ketone. But you see, the major formula for carbohydrates, it's CH2O or 2N. Yes, but then N has to be more than 3. Yes, so the least that we can think of is the triose. Right, and with the position of the carbonyl group, if it's surrounded by carbons, then that's a ketone. If it is at the end, then that's an aldehyde. Alright, and then one thing too that we will look at is isomers, stereo isomers, epimers, enantiomers, optical isomers, and also anomers. Right, so with still on the nomenclature, the carbohydrates are hydrates of carbon. So the chemical composition CH2ON, where N is more than 3. So monosaccharides, simple sugars, oligo, few, usually 2 to 10, and then polysaccharides are polymers of the simple sugars. So for monosaccharides, like I said, we have the aldehydes or the aldoses and the ketoses containing aldehyde and ketone functional groups, respectively. So the triose, if it is 3, the triose 4. So those denotes the number of carbons, and aldoses with 3 carbons are more, and then ketoses with 4 carbons or more are chiral. So with the chiral carbons you're dealing with, you have the 3 carbon groups surrounding them. Alright, so isomers, like I said, that's like the major umbrella under which you have your stereoisomers and epimers, which there's just a change on only the one carbon, which could be, and then the enantiomers could be D or L, where you have your penultimate carbon farthest away from the group, having the OH either to the left or the right. And then you can think of optical isomerism, where plain polarized light through a prism is passed through, and if it moves upwards on the left side, that is L, level rotatory, and if it is downwards or right, dextro rotatory. And the cyclization of the monosaccharides too will lead to anomerism, where an anomer where you have your P10 alpha, and alpha, that is when you have your OH down and in between the glycosidic bonds, and then beta when you have your OH up in between the glycosidic bonds. Alright, so glucose and fructose are isomers and their structures are different, but their chemical formulas are the same, which is C6H12 and O6. The two sugars that differ only in the configuration around one carbon are called epimers. Okay. And with the epimers, glucose, D-glucose, you can think of D-mannose as an epimer of D-glucose, as for D-mannose it's just an epimer at carbon number 2, where your OH, which is supposed to be at the right, is rotated to the left, and then D-galactose is at carbon number 4, where there's an epimer at carbon number 4, where you have your OH moving from the right to the left. With the cyclic monosaccharide structures and the anomeric forms, see that glucose, which is an aldose, can cyclize to form a cyclic hemiacetal, and fructose, which is a ketose, can also cyclize to form a cyclic hemiketal. So the cyclic form of glucose is pyranose, and then the cyclic form of a fructose is furanose. So the cyclization leads to pair of stereomers, which are what we call anomers. So either hemiacetal or the hemiketal carbon is known as anomeric carbon. And for these sugars, alpha OH, like I said, you have the OH down, and then the beta you have it up or left. For pyranose and furanose, see the cyclization of D glucose, you can think of alpha D gluco pyranose, and it's alpha and it's D and it's glucopyranose. So alpha, you have your OH down at carbon number 1, and then D, so the penultimate is an enantiomer, so penultimate carbon, have your OH to the right, and then so that's for alpha D glycopyranose. When we talk about the bonds between this and other glucose 2, that's when you can think of alpha 1 3 or 1 6 or whatsoever, or beta 1 6 or what. Alright, so with the beta, another one you can think of is beta D glucopyranose. So our carbon number 1 OH is up, and pyran is there. Of course, there's another cyclic form you can think of. Then D-fructose 2, if you have your OH up, that is alpha, but this at carbon number 2, you have your CH2OH up, and that's your and you have your penultimate hydroxyl OH group at the right. Then that's alpha D fructofuranose, and for beta D fructofuranose, that one. So it's not like you have just the OH. Um, you have your OH down, of course, like the same rule, that is alpha. You have your OH up at the first carbon, yeah, that is beta. That's furan, the cyclic form. So with the monosaccharide derivatives, reducing sugars with free anomeric carbons, they will reduce oxidizing agents such as the peroxide, ferricyanide, and some metals like copper and ash. And these redox reactions convert the sugar to an acid. So glucose is a reducing sugar, so the reactions are the basis for diagnostic tests of blood sugar. Alright, and for ketosis, the ketosis isomerized to aldoses under certain conditions used for these oxidation reactions with copper ions, and they also act as reducing sugars too. Alright, so the D-glucose glucose linear form, you have D-gluconate, and the sugars on mild reduction produce sugar alcohol like sorbitol, mannitol, xylitol. They are used to sweeten sugarless food products. With the disaccharides, they contain glycosidic bonds, and let's take an alpha D glucose and beta D glucose. Through hydrolysis and condensation, you form the glycosidic bond, and it can no longer open up or be reducing. That is for, let's say, alpha D glucopyranosal 1,4-D glucopyranose. Yeah, so that is the final structure that's being formed. Like I said, alpha, you have your OH down, hydrogen. Yeah, so your hydroxyl groups but oxygen down, and you have your HH up. With polysaccharides, which are also known as glycans, they function as storage structures, and also aid in recognition. Within nomenclature could be homopolysaccharide or heteropolysaccharide, and the starch and glycogen are storage molecules. For chitin and cellulose, they are structural molecules, and cell surface polysaccharides are recognition molecules. Right, so the structures and roles of some polysaccharides. Amylose, for instance, is a homopolysaccharide, but most, and they all fall under the bigamrela starch, which is energy storage in plants. So amylose homopolysaccharide, and the repeating unit is alpha-1,4 glycosidic bonds, which is linear. You have the number of monocytes or monosaccharide units are 50 to 5,000. Amylopectin is also homopolysaccharide. You have alpha-1,4 glycosidic bonds with alpha-1,6 branches every 24 to 30 residues. and with the size, the number of polysaccharides is up to 10 raised to the power 10. A glycogen homopolysaccharide, that one too. You have your alpha 1 4 glycosidic and alpha 1 6 branches every 8 to 12 residues up to 50,000 monosaccharide units, and also function as energy storage in bacteria and animal cells. For cellulose, it's also homopolysaccharide with beta 1 4 glycosidic bonds and up to 15,000 monosaccharide units, and it functions as structural functions in plants, gives rigidity and strength to cell walls. And for chitin, also homopolysaccharides, you have your beta 1 4 glycosidic bonds and NAC2. They are very, very large when it comes to monosaccharide units, and with the structures in insects, spiders, crustaceans, it gives rigidity and strength to the exoskeleton. Peptidoglycan is heteropolysaccharides, so having peptides attached, and with the repeating units, you have your MER 2 AC beta 1 4 glycosidic bonds, and NAC beta 1. The monosaccharides are very large for peptidoglycans and also function in structural ways in in bacteria. It gives, and also in other microbes, gives rigidity and strength to the cell envelope. And for hyaluronate, the glycosaminoglycan is also hetero polysaccharide and acidic. The one to have your beta 1 3 glycosidic bonds with the GLCNAC beta 1 linked to beta 1 4 to the first residue of the next disaccharide units, and has up to 100,000 monosaccharide units, and also has structural functions in vertebrates, extracellular matrix of skin, connective tissue, viscosity and lubrication in joints too. For starch, is a plant storage polysaccharide, and the two forms are amylose and amylopectin, and most starches tend to 30% amylose and 70 to 90% amylopectin, and the branches in amylopectin every 12 to 30 residues. The branches 1 6 in linkage, and amylose has alpha 1 4 links and 1 reducing end. So why is there branching in starch? You consider phosphorylase reaction. The phosphorylase enzyme releases product of 1 phosphate glucose 1 phosphate products from the amylose or amylopectin chain, and the more branches, the more sites for phosphorylase attack. So the branches provide a mechanism for quick release or storing of glucose units from metabolism. With glycogen is a storage device, and it's like storage in animals, glucose in animals. And the glycogen content in the liver may reach about 10% of its net weight. Glycogen constitutes up to about 10% of the liver mass and 1 to 2% of muscle mass, and glycogen is stored energy in the organism. The only difference from starch is that the number of branches, alpha 1 6 branches every 8 to 12 residues, amylopectin 12 to 30, and the more branch it's more branch than amylopectin. And for glycogen, it gives a red violet color with iodine. Right, so that's just a summary of how we remember on carbohydrates based on the mind map. Continue with the rest later.